In this video, I'll be going through my notes on NCEA Level 3 electrical systems. A link to the PDF and a list of corrections is in the video description. Direct current. Current is the flow rate of charge, measured in amperes, symbolized by capital A. Putting this mathematically, our current, symbolized by I, is the charge per time. Conventional current direction is defined as the direction of positive charge flow, which is opposite to the direction of negative electron flow. And so although the actual things are flowing in this direction, we define the current as being in the opposite direction, for historical reasons that are too annoying to change. And now, although changes in current travel at 3 × 10⁸ meters per second, which is the speed of light, electrons themselves only travel at millimeters per minute. To explain this, consider opening the tap on a hose pipe. Although it may take several seconds for an individual particle to travel through the hose, if the hose is pre-filled, water will flow from the end almost immediately. This is why, although electrons travel very slowly, if you had a light bulb and a switch, although the electrons flow very slowly, the changes in current flow very quickly because our conductor is pre-filled with electrons. So you could think of this as the speed of the electrons, whereas this is the speed of them bumping into each other. Let's now use this in an example. 480 coulombs of charge pass through a lamp in 2 minutes. Calculate the current through the lamp. So we know our charge is 480 coulombs, and we have a time of 2 minutes, which is 120 seconds. Current is charge over time. Putting in those numbers gives us 4 amps. For another example, a cell phone battery advertises 3,200 milliamp hours of charge. How long would it take to charge this battery from empty using a current of 2 amps? So our charge is 3,200 milliamp hours, which, although is a kind of confusing looking unit, is really just 3,200 milliamps multiplied by an hour, which is 3,600 seconds. That together gives us 11,520 coulombs. Now we know that our current is 2 amps. To find the time, we can take our current equation, swap our I and our T around, put in our numbers, which gives us 5,800 seconds. Voltage. Voltage is the energy lost or gained per charge between points in an electric field. We measure it in volts, symbolized by a capital V. As an equation, we can write that the voltage is equal to the energy divided by the charge. And so if we had a positive charge of 1 coulomb within an electric field, if by moving this charge between 2 points, we gained 10 joules of energy, 10 joules divided by 1 coulomb gives us that the voltage between these 2 points is 10 volts. The voltage across the lamp below is 12 volts. This means each coulomb of charge delivers 12 joules of energy. Ohm's law. Charges moving through a conductor encounter resistance. The amount depends on the shape and structure of the material. So for example, for shape, a thinner wire is going to have a higher resistance than a thicker wire, because a thinner wire has less room for the electrons to flow through. And an example of structure would be having a wire made out of copper rather than a wire made out of aluminium. Copper has a lower resistance, making it a better conductor. However, aluminium is cheaper. For that reason, an expensive wire is likely to be made of copper, whereas a cheap wire is likely to be made of aluminium, sometimes with a copper coating to trick the consumer. We measure resistance in ohms, which has the symbol capital Omega. When a voltage is applied to a conductor, the resulting current is limited by the resistance. This relationship is called Ohm's law. Mathematically, we can write that the voltage is the current times the resistance, where for the same amount of voltage, an increase in the resistance is going to result in a decrease in current. In an example, if we had a 12 volt source and a 6 ohm resistor, using our Ohm's law, our voltage of 12 and resistance of 6 means that we must have a current of 2.
Here I have a section of wire suspended between two retort stands. I have bits of paper draped along the wire to better see its motion. When a voltage is applied, we see the wire sag. This happens because as the voltage is applied, current flows through the wire. Due to the wire's electrical resistance, the wire heats up. As it heats up, the metal expands and the wire droops.
Equivalent resistance. Multiple resistances in a circuit can be combined into a single equivalent resistance. This equivalent resistance depends on the configuration of the resistors. For resistances in series, the equivalent resistance is just the sum of the resistances. In this case, adding resistors increases the resistance. However, for resistors in parallel, the equation becomes 1 over the equivalent resistance is the sum of the 1 over resistances. In this case, adding resistors decreases the resistance. And while the idea of adding another resistor seems like it should intuitively increase the resistance rather than decrease it, the most important thing isn't that we've added a resistor, it's that we've added an additional pathway for current to flow. And that no matter how bad a pathway this is, because it will still allow more current to flow, the total resistance of the circuit must decrease. Let's use this in an example. We have two resistors, one of 10 ohms and one of 20, connected together in parallel, which are then connected to a 5 ohm resistor in series. Calculate the total resistance. The first thing we need to do is calculate the resistance of the parallel branch, which is this thing here. To do that, we know that 1 over the equivalent resistance is the sum of the 1 over resistances. Solving that for our equivalent resistance by going 1 over both sides, or in other words, taking the inverse, gives us 6.67 ohms. Now that we know that this is 6.67 ohms, to find the total resistance, we effectively just have two resistances in series, which we can add together to find 12 ohms to two significant figures.
In this experiment, we're going to see what happens when we combine bulbs in series versus when we combine them in parallel. Starting with one bulb, we get a current of roughly 320 milliamps. Adding a second bulb, we see the brightness decrease, and the current reduced to roughly 250 milliamps. With a third bulb, our current reduces further to 205, and our bulbs are significantly dimmer. Repeating this for our parallel circuit, with one bulb we see a current of 0.34. Adding a second bulb we get a current of 0.72. And with 3 bulbs our needle goes off the scale. To summarize these experiments, adding bulbs in series increases the resistance and reduces the current. This happens because the bulbs share a single pathway, and each added bulb increases the resistance of that pathway. For our parallel circuit, it was the other way around. For each added bulb, the resistance decreased and the current increased. This happens because each added bulb is added on its own pathway, with a resistance and current that is independent to the others. And so our total current increases because there's more pathways through which it can flow.
Internal resistance. Voltage sources contribute to the resistance in a circuit due to their own internal resistance. We can therefore represent a power source as an electromotive force, symbolized by the Greek lowercase epsilon, and resistor in series. So before, when we've looked at a power supply, we've just viewed it as a voltage source. What we now need to recognize is that these power supplies have their own internal resistance. And so essentially what we have is our power supply is outlined in orange, and that power supply consists of an electromotive force, or in other words a voltage source, and an internal resistance. So you can think of this as one component, our power supply, with two separate properties. When a current flows, the voltage consumed by the internal resistance is IR. The reason we know that is if we just treat this here as a normal resistor, then the voltage across it is just going to be equal to IR, which is just Ohm's law. We can therefore write the overall terminal voltage, whereby terminal voltage, I mean the voltage across the entire component, if you were to put a voltmeter here, as the terminal voltage is the electromotive force minus IR, which is the voltage lost to the internal resistance. And so this is like the overall voltage is the voltage supplied by our electromotive force minus the voltage lost to our internal resistance. Let's use this in an example. A battery with a 12-volt EMF produces 0.5 amps of current when connected to a 20-ohm lamp. Calculate the internal resistance of the battery. And so we have our 12-volt EMF in series with our internal resistance, the value of which we are trying to find, and that is in series with our lamp of 20 ohm resistance. And as we're told, the current flowing is 0.5 amps. To start with, we can find the voltage across our lamp because we know the resistance across it and the current through it. This is useful because this voltage is also our terminal voltage. That is to say, if we were to put another voltmeter and put it across our terminal, then the value on both of these voltmeters would be the same because there's nothing but conductor between their probes. So to find our terminal voltage / our voltage across the lamp, we just use Ohm's law, V equals IR, put in those numbers, which gives us 10 volts. And now we know our terminal voltage is going to be our EMF minus IR, the voltage lost to our internal resistance. Because we're trying to find the value of internal resistance, we can solve this by subtracting the EMF from both sides and swapping them around, and then dividing both sides by negative I. Putting our numbers in gives us 4 ohms. Kirchoff's current law. The total current into a node must equal the total current out. So in other words, the current in is equal to the current out. For example, if we had our node here, which is another word for an intersection of wires, if we had a current of 12 amps and 3 amps going in, that gives us a total of 15 amps in, which means our outgoing current of 7 and 8 amps must also add to 15, such that the current in is equal to the current out. This is really just another statement of conservation of energy. Here I have a 4-way junction with multimeters displaying the current through each branch. Kirchoff's current law tells us that the sum of these currents should equal 0. For DC current, these multimeters measure to an accuracy of 1.2%. Adding the currents and their uncertainties gives a total current of negative 0.03 plus or minus 0.19 milliamps, which with an uncertainty is effectively 0. Kirchoff's voltage law. All the voltages in a circuit loop sum to 0. And while this is a simple enough statement, the analysis it requires is a little bit more complex. So for example, if we had this circuit here with a 6-volt source connected to a resistor that is consuming 2 volts, in series with another resistor consuming 8 volts, and then all of that in parallel with another voltage source providing 8 volts. Looking at this circuit, we can define 3 loops. The first loop is this one here, the second loop is this one here, and then we can do the outside loop. And now to sum the voltages in each loop. In general, when you have a voltage source, you add that voltage, and when you have a resistor, you subtract the voltage. However, there are 2 exceptions where you need to swap that around. In this example, I'll be showing you both of them. Starting with loop 1, if we decide to start here and move around in our loop, we first encounter 6 volts. However, the orientation of this power supply is such that the positive plate is here, which is subtracting energy from our incoming positive current. And so our first exception is that if a power supply is opposing the current, then instead of adding it, we subtract it. So this voltage source opposes the current, and so it's negative. Continuing around, we encounter our 2-volt resistor, which is subtracting 2 volts from our current, and then continuing around from there, we encounter our resistor of 8 volts, and while we would usually subtract this because it's a resistor, because the current is in the opposite direction to our analysis, we instead add this value. So the current is in the opposite direction, so this becomes positive. That completes our loop, and so all these values must sum to 0. And so in this example, we chose to go in this direction here to do our analysis, though it's important to note that it's just as correct to have gone in this direction here. All it would mean is that these things would be positive and this thing would be negative, such that they still add to 0. Now looking at our loop 2, we can start here and we first encounter our 8 volt voltage source, which is going in the direction of the current, and so it's adding voltage. Continuing around, we encounter our 8 volt resistor, which subtracts 8 volts from our current, and our loop is completed, and so these sum to 0. For our outside loop 3, we'll once again start here and encounter our 8 volt power supply. We next encounter our 6 volt power supply, which because it's opposing the current, it is negative, as it was in loop 1. We then encounter our 2 volt resistor, which is subtracting 2 volts from our current, and that completes our loop, and so all of that sums to 0. Here is a circuit with a 9 volt battery, 6 volt battery, and 2 resistors. We can define 3 loops in this circuit: loop 1, loop 2, and loop 3. Note that these 6 and 9 volt batteries are in opposition. Kirchoff's voltage law tells us the voltages in each loop should add to 0. In loop 1 we have 9.29, minus 6.83, minus 2.399, which totals 0.06 volts. In loop 2, the equation is the same. Although 0.06 isn't 0, it's small enough to blame on the otherwise ignorable resistance of the wires. In loop 3, we must switch the polarity of this multimeter to match it to the other, which gives 6.83 minus 6.83, giving us our expected total of 0. Capacitors. Capacitors store energy in electric fields, as opposed to batteries which use chemistry. Whereas batteries provide a roughly constant voltage regardless of their charge, capacitor voltage is directly proportional to its charge. And so 2 common types of capacitors that you might encounter is an electrolytic capacitor and a ceramic capacitor. However, at this level of study, we're only going to be looking at a parallel plate capacitor because it is the simplest case. And so a parallel plate capacitor is literally just 2 parallel plates, one with a positive charge and one with a negative charge. Between these charges is an electric field, which, as you might recall from NCEA Level 2, is parallel between the plates and curved at the edges. Furthermore, electric field lines always point towards negative. Capacitors are able to charge and discharge much quicker than batteries, but have less capacity. Capacitor capacity is called capacitance, which we measure in a unit called farads, symbolized by capital F. Specifically, the capacitance is the amount of charge stored per volt applied. So, as an equation, our capacitance is charge divided by voltage. Let's use this in an example. A capacitor connected to a 12 volt voltage supply stores 0.012 coulombs of charge. Calculate the capacitance of the capacitor. And so what's happening is that our 12 volt supply is providing enough energy for 0.012 coulombs of charge to accumulate on our capacitor. You might recall our capacitance is charge over voltage. Putting in those numbers gives us 1 times 10 to the minus 4 farads. Here I have a bar of aluminium and an ultracapacitor. This is a capacitor with a low voltage, meaning that I can place my hand across the terminals and no current will flow, but what it does have is a very high capacitance, and therefore the ability to create a very high current flow. Dielectrics in capacitors. A dielectric is an electric insulator that allows the separation of charges within itself, via which electric energy can be stored. Dielectrics are used in capacitors to physically separate the opposing plates and increase the capacitance. So if we have our parallel plate capacitor, we can slap a dielectric in between the plates, which is outlined in orange, and within that dielectric, our positive and negative charges are able to be pulled apart, and within that separation, energy is able to be stored. The effectiveness of a dielectric is described by its relative permittivity. Examples of materials and their relative permittivity: for a vacuum and also air, the relative permittivity is about 1. In reality, for air, it's a little bit higher than 1. However, the difference is so small that we might as well just call it 1. For paper, it's about 1.4, glass is much higher, as is rubber, and water has a very high relative permittivity. The capacitance of a capacitor can be increased by increasing the plate area, which creates more room for charges, so we have an increased capacity, decreasing the separation, because less distance means a stronger attraction, and if we have a stronger attraction, that means more charges are able to be pulled onto the plates. And we could also increase the permittivity, which means we have more separable charges within our dielectric, which causes a stronger attraction. Mathematically, we can write the capacitance as epsilon naught, which is a constant called the vacuum permittivity, multiplied by our relative permittivity, times our area, and divided by our separation. Now, as a side note, our vacuum permittivity multiplied by our relative permittivity is what gives us our total permittivity. And so essentially what we've done is, instead of giving all of these an ugly number, which would be something times 10 to the minus 12, what we do is just make one ugly number and then scale that by a nice amount, such as 1, 1.4, 5, 7, or 80. If a capacitor's separation is increased while it's connected to a voltage source, recalling that our capacitance is this equation here, if we increase our D, you can see that our capacitance C decreases. And now recalling that capacitance is charge over voltage, because we're still connected to the voltage source, our voltage remains constant, so that if our capacitance has decreased, then so too must our charge. If the capacitor is instead disconnected while the separation is increased, then as before, our distance increases so our capacitance decreases. However, because our voltage source is disconnected, the charge is unable to decrease because it's unable to flow anywhere, so our charge remains constant, and therefore if our capacitance has decreased, then our voltage must increase. Let's use this in an example. A parallel plate capacitor with 2.00 times 10 to the minus 3 meter square plates, 5.00 times 10 to the minus 4 meters apart, and a dielectric consisting of paper with a relative permittivity of 3.5 is connected to a 12 volt power supply. Calculate the charge stored by the capacitor. And so we're given these values here. We know our equation for capacitance, where we know all of these values, which gives us 1.24 times 10 to the minus 10 farads. Now to find our charge, we can recall that the capacitance is charge over voltage. Rearranging that for charge, putting our numbers in, gives us 1.49 times 10 to the minus 9 coulombs. I have here an electrolytic capacitor, which we can delicately dissect by exceeding its breakdown voltage, creating a short between the anode and cathode, rapidly heating the electrolytic fluid, producing gases, and blowing the capacitor to bits. Sifting through the debris, we can identify the rubber stopper, aluminium anode plate with an oxidized layer serving as the dielectric, a layer of electrolyte soaked tissue, now obliterated, acting as the cathode, the outer housing, and the melted plastic coating. Charging and discharging capacitors. The charging and discharging of capacitors follow an exponential curve. We further quantify this by defining the time for a 63% change as the time constant tau, the same symbol that we use for torque. Time constant, which is measured in seconds for a resistor-capacitor circuit, is just the resistance times the capacitance. And so if we're charging a capacitor, if we look at the voltage curve, we're going to start at 0 and increase to our maximum voltage. The time for that to increase to 63% of its maximum is our time constant tau. And as you can see, our voltage increases rapidly to start with, indicating that we're starting at our maximum current. As the change in voltage decreases over time, that means our current must be doing so as well. The reason for this is that initially when our capacitor is uncharged, the charges are able to race on unaffected. However, if we have our capacitor already with charges on the plates, then the incoming charges will experience a repulsive force. That repulsive force increases as the capacitor charges, and so the current decreases. The time for our current to decrease by 63% is our time constant tau. And so current slows as the increasing capacitor plate charge increasingly repels new incoming charges. For discharging a capacitor, the voltage starts at a maximum and then decreases to 0. The time for a 63% drop is our time constant tau. And for current, the current is initially high as the plate charges repel each other from the charge-dense capacitor plates. And so if we have our capacitor plates, which are fully charged, then the high density of charges is going to result in a large repulsive force between the charges, and so sort of like a spring coiled up, when that's released, we're going to have a large amount of movement initially. And so our current starts at a maximum once again, and then decreases to 0. The time for a 63% drop is once again our time constant tau. So in all cases, the time constant is the time for a 63% change. Why 63%? The derivation of that requires mathematics that is above this level, as it involves consideration of the exponential function. For NCEA level 3, you just need to know this number and not where it came from. The time constant is always the time for a 63% change. If the value is increasing, it will increase to 63% of its maximum value because that change is 0 plus 63. So if we have a increasing value, the time constant is the time for it to increase to 63% of the maximum. However, if the value is decreasing, it will decrease to 37% of its maximum value. Since because it's decreasing, it's starting at 100%, and then when we subtract 63%, we arrive at 37. So if we have our decreasing value, when we've decreased by 63%, what's left is 37% of the maximum. If we consider a circuit with a voltage source, a resistor, and a capacitor in series, the source voltage is shared between the resistor and capacitor, such that the source voltage is equal to the resistor voltage plus the capacitor voltage. And so, over time, the source voltage remains the same, and if we were charging our capacitor, as its voltage increases, our resistor voltage decreases. This is also apparent because the current follows the same curve, and as we know, V is equal to IR, and so the voltage across the resistor is directly proportional to the current. Let's use this in an example. A 100 microfarad capacitor is charged in series with a 5 volt voltage source and 1200 ohm resistor. Calculate the voltage after two time constants. And so we know that 100 microfarads is 100 times 10 to the minus 6 farads. If you don't, then you'll need to brush up on your prefixes. We know our voltage and we know our resistance. We know that time constant is resistance times capacitance for a resistor-capacitor circuit. Knowing those numbers gives us 0.12 seconds. And so if we graph this situation, as our capacitor charges, our voltage increases. The voltage after one time constant is going to be 63% of our maximum voltage, which is 3.15 volts. The remaining voltage is our maximum minus this 3.15, which is 1.85. The reason we need to know this is that to find the voltage after two time constants, we basically reset the graph here, where our voltage after two time constants is at 3.15 volts plus 63% of the remaining voltage. That gives us 4.32 volts. Energy in a capacitor. When charging a capacitor, the energy supplied is equal to our charge times voltage, and since we know that Q is equal to CV, and the reason we know that is that our capacitance is charge over voltage, then making that substitution we get CV squared. And now what might be a surprising statement is that half the energy supplied is lost to the resistance. Let's now talk about why. As the capacitor charges, the current decreases from its maximum value to 0. Because resistor voltage is proportional, it does too. So if we graph our resistor voltage against our capacitor charge, recall that the resistor voltage is equal to current times the resistance. Our resistance stays the same, and as our capacitor charges, the current decreases. Because the resistor voltage is proportional, it must decrease as well. And furthermore, the area underneath this graph is equal to the energy lost by the resistance. The capacitor voltage increases in proportion to the decreasing resistor voltage. Graphing our capacitor voltage against capacitor charge, as the capacitor charges, its voltage of course increases. And once again, the area underneath this graph is the energy, and specifically the energy stored in the capacitor. And so, looking at these graphs, we can see that the overall voltage supplied is split between the resistor and the capacitor. As voltage is energy per charge, the energy supplied is also split, such that the energy stored in the capacitor is half of our energy supplied, specifically half times QV, or half times CV squared. Capacitors in circuits. As with resistors, we can replace multiple capacitors with a single equivalent. The value of this equivalent depends on how they're connected. For capacitors in series, 1 over the equivalent capacitance is the sum of the 1 over capacitances, and for capacitors in parallel, the equivalent capacitance is just the sum of the capacitances. You might note that this is the same mathematics we use to combine resistors, except these are swapped around. I have here 3 capacitors with individual capacitances of 0.485, 0.486, and 0.487 microfarads. The multimeter used measures capacitance in this range with an uncertainty of 3%. When combined in parallel, capacitances add together, which would give a capacitance of 1.46 plus or minus 0.04 microfarads. Doing this practically, we get 1.44 plus or minus 0.04 microfarads, agreeing within uncertainty. When combined in series, the inverse of the combined capacitance is equal to the sum of the inversed capacitance, which would give a capacitance of 162 plus or minus 4 nanofarads. Doing this practically, we get 169 plus or minus 5 nanofarads, once again agreeing within uncertainty. Magnetic flux. We can describe the amount of magnetic field passing through a surface as magnetic flux. It has units of Webers, symbolized by capital W lowercase b. The maximum flux occurs when the field is perpendicular to the area, like we see here. In this case, the maximum flux is equal to the magnetic field multiplied by the area. However, if the field is instead at an angle theta to the perpendicular, the flux is reduced. And mathematically we have the same relationship, except now multiplied by cosine of the angle. You might note that for our above situation, the angle is 0, and so if we take this equation and make this cosine of 0, you might note that cosine of 0 is 1, and so we just get this equation here. Faraday's law. Changes in magnetic flux induce EMFs or voltages equal to the rate of change. And so our induced EMF is equal to negative the change in magnetic flux divided by the duration over which it changed. The negative sign indicates that the induced EMF is in opposition to the changing flux. Similar how, if you recall Hooke's law, we had F is equal to negative kx, where that negative indicates that the restoring force is always in opposition to the displacement. And now if we were to graph the flux and the EMF over time, if our area is parallel with the field lines, then our magnetic flux is 0, and because the slope of our magnetic flux here is at its greatest, then we have the greatest rate of change of flux, and therefore a maximum EMF. In the situation where our area is instead perpendicular, then we have a maximum amount of flux, or in this case a negative maximum. Because this is a turning point, the slope is 0, and therefore our rate of change is 0, and therefore our induced EMF is 0. Once again, when our area is perpendicular, we once again have no flux, a maximum rate of change, which means another maximum EMF, in this case a negative maximum. And now as our area is once again perpendicular, we have a maximum flux, in this case a positive maximum, at which the rate of change is 0, and therefore our induced EMF is 0. And so on. Let's use this in an example. A 0.25 meter square loop of wire is rotated once per second in a 12 Tesla magnetic field. Calculate the EMF induced in the coil. And so our area is 0.25 meter square, and our magnetic field is 12 Tesla. Our maximum flux is just going to be these two multiplied together, which gives us 3 Webers. And now our magnetic flux, because it rotates once per second, changes from 0 to its maximum in a quarter of a second. The reason for this is because we know that this here is 1 second, and that if we divide these into 4, we see that we go from our 0 flux to our maximum flux in 1/4 of this second. And so our change in flux is from our maximum to 0, which is just 3 Webers, and our period is a quarter of a second, which is 0.25 seconds. So our EMF is negative our change in magnetic flux over time, putting in those numbers, gives us negative 12 volts. Once again, the reason that this is negative is because we have a positive change in flux, which means we must have a negative change in EMF. Here I have a plastic cup with foil strips down opposite sides, filled with foil balls, connected to an LED and a 3-volt battery. The LED is initially off, as the foil balls do not have sufficient contact to complete the circuit. However, by igniting a barbecue lighter nearby, we see this change. It can't be the heat or the gases produced, as it works with the lighter under the table. It isn't triggered by sound, so it must be the spark. We can further verify this using a Wimshurst generator, which generates pure sparks, strong enough to produce the effect at a distance of 10 meters. To answer how this works, electrical discharges produce electromagnetic waves, which induce currents in metals. According to this paper, the current flowing through these spots generates local heating, which leads to an increase of their contact areas, and thus enhances their conduction. This current-induced temperature rise, up to 1050 degrees Celsius, results in the micro-welding of contacts. This is called the Coherer effect. Lenz's law. When a coil of wire, also called a solenoid, experiences a changing magnetic field, a current is induced in opposition to the change. And so if we move the north pole of a magnet towards a solenoid, the solenoid will experience an increasing magnetic field, which will induce a current within that solenoid. One way to figure out the direction of the current is that if it's north towards, you can draw a capital N, and then put arrows on the ends of the letter, which show that we have an anti-clockwise current. And now as a result, our coil of wire behaves like an electromagnet with the north pole here and the south pole here, such that it opposes the approaching magnet. So to bring the magnet closer, you need to expend work against this force, and that energy is what is used to establish this current and magnetic field. For the opposite case, where we have a south pole coming towards the solenoid, a current is once again induced, and we can instead draw a capital S and put arrows on the ends, which indicate a clockwise current. And now if instead you're moving the north away and the south away, the situation is reversed. Where in this case here, note that our electromagnet is behaving like a magnet with a south pole here and a north pole here, such that as you try to move the magnet away, the south pole attracts it. And so in each of these 4 examples, the current and magnetic field induced in the solenoid is trying to oppose this change. If you're trying to bring the magnet towards the solenoid, it's going to repel it, and if you're trying to take it away, it's going to attract it. Note that this effect is only present while the magnetic flux is changing, which is only the case while the magnet is in motion. So if the magnet isn't in motion, we don't have a change in magnetic field, and therefore we don't see any effect. This is a St. Louis motor. As current flows through the coil, it establishes a magnetic field. The permanent magnets interact with this field, producing a force that causes the coil to rotate. When the coil reaches halfway, a slotted conductive ring is designed to reverse the current, which reverses the field in the coil, reversing the forces, allowing the coil to continue in the same direction, and so on. Replacing the power supply with a voltmeter, instead of using electricity to spin the coil, we can spin the coil to produce electricity. Here I have 2 plastic rollers, a thick bar of copper, a disc that isn't magnetic, and a disc that is. Waving the non-magnetic disc above the plate has no effect, whereas the magnetic disc produces a non-contact force. Because copper isn't magnetic, this effect must be partly electric. What's happening is that as the magnet passes the copper is experiencing a changing magnetic field. This changing magnetic field produces an electric current. This current produces a magnetic field, which interacts with the original magnetic field of the magnet, producing a repulsive force between them. With another copper plate, we can perform a variation on this experiment. The non-magnetic disc falls without intervention, whereas the magnetic disc is slowed in its descent. Self-inductance. Self-inductance is a measure of how effectively a conductor induces a back EMF in itself. It is measured in Henry. So how can a conductor induce a back EMF in itself? Consider if the current changes in the conductor. So if our current increases, this is going to cause a changing magnetic flux in itself. So our magnetic flux is going to get greater, which induces a back EMF, opposing the original change in current. And so when a conductor experiences a changing magnetic flux, even if it is itself that caused that magnetic flux, it's going to experience a back EMF. The value of that back EMF is equal to the self-inductance multiplied by the changing current over the duration, where once again this negative sign here indicates that our back EMF is in opposition to our change. Inductors. An inductor is a component that is designed to have a particular self-inductance. Here are a few examples, which you might note are just coils of wire arranged in different ways. Due to this self-inductance, inductors produce a back EMF in opposition to current changes in their circuit, slowing down these changes. So essentially, inductors make the changes in a current more sluggish. If the current through the inductor is constant, no back EMF is produced. So if there's no current change, there is no back EMF. The symbol for an inductor is this here. And so if we graph the current and EMF over time, if our current increases, we're going to see a EMF in opposition to that increase. And then as our current reaches a constant value, we're going to see no EMF. And then as our current decreases, we're going to see an EMF once again. The EMF is now half the size because the current has changed by the same amount, but in double the time. And it's important to note that when we have a positive change in current, we have a negative EMF, and when we have a negative change in current, we have a positive EMF, such that the EMF is always in opposition to the change. Inductive factors. The inductance of an inductor is increased by several factors. So if we take our inductor and we add more coils, the inductance increases because we have more coils interacting with the magnetic flux. More coils, more effect. And if we add more area, then we have more inductance because more area requires more coil, and more coil means more interaction with the magnetic flux. We could also make our coil tighter. Because the distance between the coils is reduced, the coils are more closely affected by each other's magnetic flux. And lastly, we could add a core, which allows the magnetic flux to conduct with less losses. Essentially, it behaves like a conduit. Inductor energy. While current flows through an inductor, it stores energy in the form of its magnetic field. So if we have current flowing through our inductor, it's going to establish a magnetic field within which we have energy stored. More current means a stronger field, which means a higher amount of energy. And so the equation for the energy stored in our inductor is half the inductance times the current squared. Here I have two magnets suspended from identical springs. The magnets are positioned to oscillate through a pair of solenoids, which are connected through a switch. Setting the left magnet oscillating with the circuit initially open, nothing happens. Closing the switch, the right magnet begins to oscillate as well. This happens because the oscillating magnet creates an alternating flux in the left solenoid, inducing an alternating current in the circuit. This alternating current produces an alternating magnetic field in the right solenoid, exerting an alternating force on the right magnet, causing it to oscillate. Inductor time constant. Similar to a capacitor, the current and voltage change in an inductor follow an exponential curve. We can once again define the time for a 63% change as the time constant tau, where in this case our time constant is the inductance over the resistance. For charging our inductor, if we graph our voltage and our current against time, our current increases from 0 to its maximum value, and the time for it to increase by 63% is, as usual, the time constant tau. The voltage or back EMF produced by the inductor is proportional to the rate of change of current. Because the rate of current change is highest initially, our voltage is going to be initially at a maximum, and then as the rate of current change goes to 0, so too will our opposing voltage. And so initially the current increases rapidly, causing a large opposing voltage. The time for this voltage to decrease by 63% is, as per usual, our time constant tau. In the case where we are discharging our inductor, graphing our voltage and our current goes from a maximum value to 0, and the time for it to decrease by 63% is our time constant tau. As with before, because our rate of change of current is the greatest initially, our voltage starts off at a maximum and then decreases to 0 as the rate of change of current decreases to 0. The time for it to decrease by 63% is once again our time constant tau. And so initially the current decreases rapidly, causing a large opposing voltage. Important to note that the voltage for our charging case and the voltage for our discharging case are in opposite directions. That's because initially we have a positive change in current, and because the back EMF is always in opposition to this change, our back EMF is negative. Whereas when we're discharging, we have a negative change in current, and so to oppose that, our opposing voltage is positive. Transformers. A transformer consists of two inductors arranged such that a flux change in one produces a near equivalent flux change in the other. This is called mutual inductance. And whereas mutual inductance is between two inductors, self-inductance, which we covered earlier, is only between one inductor and itself. A core of iron is often used to improve flux transmission. So if we have our primary coil and our secondary coil, and the amount of loops in our primary coil is NP, and for our secondary coil it's NS, a core of iron is used to connect them in the same way that we might add a core to an inductor. This allows the magnetic flux to better move from one to the other. The iron is laminated to reduce eddy currents, which cause energy losses. So if we had just one block of iron, the changing magnetic field would cause a large change in current, which would cause a lot of energy to be lost to heat. If we instead laminate this iron, then because the current cannot flow between the layers, we instead get a number of smaller currents, which amount to a smaller energy loss. Transformers are often used to increase voltage at the expense of current, or vice versa. This is dependent on the turn ratio. By turn ratio, we mean the amount of primary turns divided by the amount of secondary turns. By turns, we mean the amount of physical loops. So in this case, there are 5, and in this case, there are 9. This turn ratio is also equal to the ratio of the voltages and the inverse ratio of the currents. Charging a smartphone typically requires a voltage of 5 volts and a current of 2 amps. To charge a smartphone from a wall outlet, a transformer is required to reduce the 200 volt supply to 5 volts. Knowing this, we can determine the current from the wall outlet. And so we're wanting to charge our eggplant phone, and it requires a voltage of 5 volts, and we want a current of 2 amps. To do this, we're using a wall outlet, which produces a voltage of 240 and a current which we don't currently know. To find this current, we can recall that the ratio of the voltages is equal to the inverse ratio of the currents. Solving this for our primary current, putting our numbers in, gives us 0.042 amps. And so you can see that we have reduced the voltage in the same proportion that we've increased the current. Mathematically, we're essentially trading one for the other. Transformer efficiency. We define an ideal transformer as having no power losses, so that the input and output power are equal. In reality, energy is always lost. We therefore define the efficiency of a transformer as the percentage of the input power that makes it to the output. So our efficiency is the amount of output power as a fraction of the input power, and then multiplied by 100% to make it a percentage. I have here a transformer with 400 turns and 5.92 volts on the primary coil. In an ideal transformer, the turn ratio is equal to the voltage ratio. However, due to energy losses in the real world, we must also consider efficiency, which for this transformer is around 83%. Starting with the same amount of turns on the secondary, we expect the same voltage, or around 83% of it due to losses. Instead, the voltage is much lower. This is because the iron core is incomplete, drastically reducing the transmission of magnetic flux. Adding the missing piece, we get a much better voltage of 4.92 volts. Halving the turns roughly halves this voltage, doubling it roughly doubles it, 4 times gives roughly 4 times, and 8 times roughly 8 times. While converting 5.92 volts into 38.5 volts might initially appear to violate energy conservation, the trade-off is less current. It's like cutting a pizza into 4 pieces instead of 8. Sure, the slices are bigger, but you've got less of them, so it ends up being the same amount of pizza.
This here is a Jacob's ladder. This consists of a pair of wires that are closest near the bottom and further apart at the top. When a high voltage is applied between the wires, the air is ionized and an electrical pathway is formed. Due to its high temperature, this ionized pathway rises and lengthens as the wires move further apart. Eventually, the resistance of this pathway is great enough that it's more energetically favorable to ionize a fresh path.
AC circuits. whereas a direct current DC flows in a single unchanging direction. Alternating current, AC, unsurprisingly alternates direction. So our direct current has a constant current that doesn't change direction over time, whereas an alternating current goes from forwards to back to forwards to back, or in other words, positive to negative. And so if we had a wire and we had a direct current electron going through it, the path of that electron would be steady and wouldn't change. However, for alternating current, if we were to look at an individual electron, the path of that electron is going to go back and forwards and back and forwards. Both voltage and current follow a sinusoidal relationship, where sinusoidal refers to this pattern here. Mathematically, that means we can write that the voltage is our maximum voltage times sine of omega t, and the same for our current. All this function does is go between positive Vmax and negative Vmax over time, and the same for current. Let's use this in an example. A 50 Hz AC supply has a maximum voltage of 240 volts. Calculate the time for the voltage to reach 120 volts after the supply is switched on. So we know our maximum voltage, our frequency, and the voltage we're reaching in our unknown time. To use our voltage equation here, where we know this, and we're trying to find this, we need to find our angular frequency. To do that, we can use the equation 2 pi f, which is given to you on your formula sheet. Putting in our frequency gives us 314 radians per second. And now to solve this for our time, we first divide both sides by the maximum voltage, then take the inverse sine of both sides, and now finally divide both sides by omega. Putting our numbers in gives us 0.0017 seconds. RMS. The voltage and current in an AC circuit are changing constantly. It would be useful to describe AC voltage and current with a constant average value. Trouble is, that is always zero. That is to say, if we have our voltage changing over time, like it does with AC electricity, where this is our peak, the average is always going to be zero. To get a useful value, we instead take the square root of the mean voltage or current squared, which effectively just takes this bottom section here and makes it positive. This gives us what we call the RMS voltage. Our peak and RMS voltage and current values are proportional by the square root of 2. And recalling that power is current times voltage, multiplying VRMS and IRMS, provides us with the same power value as an equivalent DC circuit. LCR circuits. An LCR circuit consists of an inductor, capacitor, and resistor. This forms a resonant circuit where energy oscillates between the inductor and capacitor. And so we have our inductor, our capacitor, and our resistor, all of them in series. You can have parallel LCR circuits, but not at NCEA level 3, though I should note that it has popped up in scholarship. Energy is stored in the capacitor in the form of the electric field, as per usual, and it's at its maximum when the current is 0, since when the current is 0, the capacitor is fully charged. Energy in the inductor is stored in its magnetic field, as per usual. This is established when the current increases and collapses when the current decreases, and it is furthermore at a maximum when the current is also at a maximum. And so we can see that the conditions for the maximum energy for the capacitor and inductor are in opposite phases. Let's now go through the behavior of an LCR circuit step by step. If we have an LCR circuit with the capacitor initially charged, then all the energy is in the capacitor, and because our current is 0, none of it is in the inductor. Our capacitor is then going to naturally discharge, decreasing the amount of energy it stores. As it discharges, our current will increase. An increasing current is going to create a back EMF in the inductor, which is going to oppose this increase. At this point, because we have a current flowing, we have energy in the inductor. Once the capacitor is fully discharged, we have no energy stored in our capacitor, and because our current is at a maximum, the energy stored in our inductor is at a maximum. And now for the interesting bit. Because the current starts to decrease, the inductor induces a back EMF that opposes this decrease. What this means is that instead of our capacitor completely discharging, it instead overshoots and starts to charge in the opposite direction. And so because we have current, we have energy in the inductor, and because our capacitor is now partially charged, we also have energy in the capacitor. This continues until our capacitor is fully charged once again, at which point the current is 0, and so the energy stored in the inductor is 0. If we were to continue our analysis, the situation would now loop back to the start and begin the cycle once again, except with the current and the voltages in the opposite direction, because our capacitor is charged in the opposite direction. Furthermore, because we have a resistance, we're going to have some energy lost to that resistor. Therefore, the amount of energy stored in our capacitor is less than it was at the start. Phase in an LCR. As we know, in an LCR circuit, the energy and therefore the voltage in the inductor and capacitor experience maximums at opposite times. Graphing this on a sine graph, we can first graph our resistor voltage, which is useful because it's in phase with the current, since the amount of energy dissipated in the resistor is always proportional to the current, via the old trusty relationship V is equal to IR. And so graphing our VR / our current, our inductor voltage is at a maximum when the current is at its maximum rate of change here. Furthermore, our capacitor voltage is at a maximum when the current is 0 because the capacitor is fully charged. And furthermore, when the current is at a maximum value, the capacitor is fully discharged. And because we no longer have any changing current, we have no voltage induced in the inductor. Representing this as a phasor, which conventionally rotates counterclockwise, if we have our resistor voltage vector here, which represents this scenario here, then we can see that our inductor voltage is at a positive maximum and our capacitor voltage is at a negative maximum. What we can see is that our inductor voltage leads the resistor voltage by 90 degrees, and our capacitor voltage lags the resistor voltage by 90 degrees. And now, as discussed in the last page of notes, energy in an LCR circuit is gradually lost to our resistance, and so to keep an LCR going, you need a power supply. Where the power supply fits into in this phase diagram depends on the relationship between the inductance and the capacitance, which we'll alternatively think of in terms of the inductor and capacitor voltages. If our inductor voltage is greater than our capacitor voltage, then looking at our phasor diagram, once again with our resistor along the horizontal, because our source voltage is equal to the sum of the circuit voltages, we need to sum our vertical voltages. And if our VL is bigger than VC, that sum ends up positive, and our Vs leads our current. Whereas if our inductor voltage is smaller than our capacitor voltage, as we see here, our source voltage instead points downwards, and in this case our source voltage lags the current. And once again, what I mean by leading and lagging is that because this phasor diagram is rotating counterclockwise, in this case here, our Vs is ahead of our current, and so it leads the current, whereas in this case here, it's behind the current, and so it lags the current. For our last situation, if instead these voltages are equal, then our vertical component of our source voltage goes to 0, and our source voltage is entirely horizontal, meaning that our source voltage is in phase with the current. Reactance. Reactance is the opposition to an AC current caused by the inductance and capacitance in a circuit. Like resistance, reactance is measured in ohms. Unlike resistance, energy is not lost to reactance, rather it is always stored, much like we'd store energy in a spring. Furthermore, reactance can even be negative and also cancel out. Reactance is symbolized by the letter X, and the capacitor reactance is equal to 1 over the angular frequency times the capacitance, whereas the inductor reactance is equal to the angular frequency times the inductance. And if you recall that our omega is equal to 2 pi f, if we increase our frequency, we're also increasing our angular frequency, which will result in an increase in the inductor reactance and a decrease in the capacitor reactance. This behavior is very important when we consider how these circuits resonate. Let's use this in an example. A 150 microfarad capacitor is connected to a 120 Hz AC power supply. Calculate the capacitor reactance. Our capacitance of 150 microfarads is just 150 times 10 to the minus 6, and we know our frequency of 120 Hz, which since omega is 2 pi f, we can also use to find that, which gives us 754 radians per second. To find our capacitor reactance, we know that that is 1 over omega c. Putting in those numbers gives us 8.84 ohms. For another example, a 10 Henry inductor is connected to the same 120 Hz power supply. Calculate the inductor reactance. So we have our inductance and we have our omega from before. We know that the inductor reactance is omega L. Putting those numbers in gives us 7,540 ohms. Impedance. We have now learned that the current is opposed by both resistance R and reactance X. Impedance Z combines these effects into a single term. Specifically, the impedance Z is equal to the square root of the resistance squared plus the reactance squared, where if we note that our reactance is our inductor reactance and our capacitor reactance, where we have a minus because they're in opposition to each other, then we can also apply Ohm's law to each of these terms. Recalling that Ohm's law is V equals IR, we can say that our supply voltage is equal to our circuit current multiplied by the impedance. For our resistance, we just have our V equals IR, as we always have. For our inductor and our capacitor voltages, we can write the same except with the reactances, where the current in all of these cases is the same because we're looking at a series LCR circuit. I have here a bank card with the technology to perform contactless payments. To get a better look at its internals, the plastic can be dissolved in acetone, leaving behind the circuitry. Here we see a coil of wire functioning as the card antenna connected to a microchip. When a card reader is set to make a transaction, it produces an alternating current through its coil, generating a changing magnetic field, which induces an electric current within the card's coil that is used to power its microchip. The card and reader are able to change the impedance of their coils. While the coils are in proximity, a change in the impedance of one will have a measurable effect on the other, which allows for two-way communication. LCR resonance. Recall that XL and XC are inversely dependent on frequency. Recall that they have these equations here, such that if we increase our angular frequency, our XC is going to decrease while our XL increases, whereas if we decrease our angular frequency, the opposite is true. What that means is if we were to graph this reactance against our angular frequency, our XL is going to increase linearly, whereas our XC is going to decrease in an inverse relationship. This means there exists a frequency at which XC is equal to XL, which is right here. Because XC and XL are 180 degrees out of phase, they cancel out, and our total reactance is 0. Because our reactance is 0, while our resistance stays the same, this means that our impedance is at a minimum and is therefore equal to our resistance. We can see this mathematically by using our impedance equation, and if we make our reactance 0, then we just get the square root of r squared, which is just r. Because our impedance is at a minimum, that means our current must be at a maximum. So if we were to take this same graph, but instead plot our impedance and our current, then our impedance would start off large, as we have a large reactance because our XC is large. Our impedance would then reach a minimum, as our total reactance goes to 0. Continuing to increase our frequency, our impedance increases once more, to a maximum where our inductor reactance is dominant, recalling that our source voltage is equal to IZ. If our source voltage remains the same, then we can see if our impedance decreases, then our current must increase, and vice versa, so that our current starts off at a minimum, increases to a maximum, and then decreases back to a minimum. This special frequency, where our current is at a maximum, is called the resonant frequency. Let's use this in an example. A 120 microfarad capacitor and 5.6 Henry inductor are connected in series with an AC power supply. Calculate the resonant frequency of the circuit. Our capacitance of 120 microfarads is just 120 times 10 to the minus 6, and we of course know our inductance. If we are at our resonant frequency, that means our reactances are equal. We have equations for each. Where to find the resonant frequency, we need to solve first for our angular frequency. There are a few ways we could go about this. What I'm first going to do is multiply both sides by omega, which cancels out omega here and squares the omega here. Next, to move the L onto the other side, I'm going to divide both sides by L. And now, since we know that omega is 2 pi f, we can make that substitution, where I've separated out the 2 pi squared and the f squared, dividing both sides by 2 pi squared. And now if we square root both sides, the square root of 1 is 1, the square root of 2 pi squared is just 2 pi, and we're just left with the square root of LC. Putting in our numbers gives us 6.14 Hz. I have here a series LCR circuit with an inductor, capacitor, and resistor for which I'm using a lamp. I also have an ammeter displaying the current. Sweeping the frequency of the AC supply from low to high, we see the current peak at around 222 Hz. To explain this, recall that the source voltage, which we're keeping constant, is equal to the circuit impedance multiplied by the circuit current. For there to be a maximum current, there must be a minimum impedance. Impedance is equal to the square root of the resistance squared, plus the inductor reactance minus the capacitor reactance squared. Because inductor reactance increases with frequency, while capacitor reactance decreases, there exists a particular frequency where the two are equal, and the total reactance is 0. Under these conditions, the impedance is at its minimum, equal to the resistance, and the current is consequently at a maximum. We call this effect resonance, and the associated frequency the resonant frequency. We can change the resonant frequency by changing the capacitance, for example, by swapping out the 100 microfarad capacitor for a 1 microfarad, giving us a new resonant frequency of around 1.552 kHz. We can also change the resonant frequency by changing the inductance, for example by adding a core to the inductor, giving us a new resonant frequency of 534 Hz.